Hi, I'm Samya and I'm going to be talking about speech enhancement using Kalman filter for my pattern recognition class project. So the main objective behind speech enhancement is to improve the intelligibility and the overall perception of the degraded noise, the degraded signal. It can be used in many applications such as voice control in an automotive environment, and it is basically used for improving the quality of service in speech recognition, teleconferencing systems, and hearing aids. The information conveyed by the speech signal is multi-layered and has spectral variations that convey information like emotion, age, gender, state of health of speaker, and expression. So the initial step for developing any of the speech application is to remove the noise from the signal. It is easy to observe the noise during speech pauses due to the nature of the speech signal, where we pause between two words. So it is easy to observe the noise during these pauses. The speech signal are non-stationary, meaning to say that the mean function is a function of time, and even the autocorrelation function is a function of time. The frequency content of the speech consists of many frequency components. Thus, a simple mathematical model does not help. We have to build an appropriate model for proper enhancement. Focusing now on the modeling of a speech signal. There are many models for building a speech signal, and what kind of a model we use depends upon the application. Examples of the models are the linear predictor model, the harmonic pulse noise model, and the autoregressive model. The autoregressive model is what we are going to use for building the speech signal. So what the autoregressive model does is the output is defined linearly in terms of its own previous value. And say we have a speed signal s of k, and to define the speed signal s of k at the kth instant, it can be defined as the equation shown over here, and that equation can be written in the matrix form as shown in this equation here. And if we just create a new variable, say x of k, as a vector of all the speed signal at all the instances, then we get the equation over here, and this can be written as the equation shown over here. Over here, this is the inputs vector, this is the state transition matrix, and this is the state vector. This is modeling of a clean speed signal, and we have to model it as a noisy signal, so we say y of k is equal to s of k plus n of k. And similarly, as this equation, we can define it in the matrix form as in this equation. So now we'll talk about adaptive filters. Adaptive filters are the filters where the transfer functions are controlled by parameters that are varying and updated in every iteration. So it can be used in real-time modeling tasks. And the advantages of the adaptive filters is that it gives us like optimal results, low processing delay, and better tracking of the trajectory of the non-stationary signals. Few of the examples of the adaptive filters are the linear least mean square, the recursive least square, adaptive linear filter, and Kalman filter. We are going to be using a Kalman filter for the speech enhancement. So we'll talk a bit about Kalman filter now, and basically the Kalman filter, it works on a predict and update mechanism. So it operates recursively on a set of noisy inputs to produce an optimal estimate of the speech, original speech signal. You should have the knowledge of the system and the measurement device to get a proper enhancement of the speech signal. And there have been many modified versions of this algorithm. The thing about Kalman filter is it makes a few assumptions, and due to these assumptions we get a few disadvantages. And to overcome these disadvantages, they've used other modified versions of this algorithm, and a few of them are the unscented Kalman filter model and the extended Kalman filter model. So the algorithm behind this Kalman filter seeing it from a speech enhancement point of view is that first we have to read the input file. Since we're using MATLAB for the execution of this algorithm, we use either wave read or audio read for reading the input file, and then we have to add noise to this input. And the noise considered in our case was Gaussian in nature, and we considered the case of both Gaussian noise and also um, colored Gaussian noise. And the second step after adding noise to the input signal is to initialize the matrices such as the Kalman gain matrix, state transition matrix, covariance matrix, and we have to initialize the estimated signal matrix as well. This is the equation shown in the slide is the ones for the Kalman filter model, and before we start executing this algorithm, we have to check if our input, whatever signals that we're using, fits this model. And the autoregressive modeling of a speech signal fits the Kalman filter equations, and thus we can go ahead to execute this. And so the Kalman filter, as mentioned earlier, it works on a predict and update basis. So what it does is it predicts the state of the input vector, and it also predicts the prior covariance. And after it predicts that, using these two vectors, it finds the Kalman filter gain. The Kalman filter gain is then used for updating the actual value of the state vector and the prior covariance. So the value of the covariance that we use initially can be found by using this formula right here. So these are the results that we obtained by using Kalman filter for speech enhancement. As you can see, this is the original signal right here, and after adding the noise to the speech signal, it's degraded pretty badly, and this is the estimated signal, and it's pretty close to it. It's pretty close to the original signal. And this is for the white Gaussian case, and this is for the colored Gaussian case. So the white Gaussian is over a whole band of frequency, and but colored is only for a selected set of frequency. And this is the colored noise. So I guess at this frequency band we are adding a lot of noise signal. This is the mean square error for the white Gaussian case, and previously there have been many techniques that have been used for enhancing the speech signal. Two most conventional methods are the spectral subtraction and the Wiener filter. So from this slide onwards, we'll compare these three models and see which gives us the best optimal result. So for concentrating now on spectral subtraction, the idea behind it is that we have the power spectra of an additive independent noise signal is also additive. Since noise is additive, we can add or subtract anything from the power spectra. So we have so the idea behind the spectral subtraction is to subtract the mean noise power to obtain the least square estimate of the original power spectrum. So what they do is they directly subtract the noise power from the noisy signal and try to find an estimate of the original signal. The best thing about this spectral subtraction is that there's no assumptions made, and the disadvantages are that there are instances where the noise power is more than the signal power. So when we try to subtract the noise power from the signal power, we might get a negative estimate of the power spectrum. And to overcome this issue, they just made the power spectrum to be 0 at all these instances. But the problem with this is there will be musical tones because of the other spectrum power. And there are other modified methods to overcome these issues. Next, we'll be talking about the Wiener filter. Uh, the Wiener filter assumes that whatever signal it's using is stationary in nature. Like the spectral subtraction, this method also requires an estimate of the path spectrum of both the clean signal and the noise signal, and the Wiener filter can be modeled as shown in this formula right here. The main disadvantage is that because of its stationary property, there's a fixed frequency response at all frequencies. There are other modified versions that are used to overcome these problems, and those are the adapter filter, the non-stationary filter, etc. These new versions, they give us optimal results in the least square error sense. But the problem is none of these models, they exploit the speech production model as the Kalman filter model. So having comparing all these three techniques, the spectral subtraction, it has like the least performance in a very high SNR case, and this is due to because the phase errors, the magnitude errors have been neglected. But in the high SNR case, it does provide good results and it is very efficient. Uh, the problem with Wiener filter is that it degrades due to the non-stationary property of the speech signal, and compared to the other two models, Kalman filter is provides us the best optimum result, and it overcomes all the problems stated in the other two algorithms. This is a comparative study done in one of those research papers that I borrowed the results. So you can see that this is the SNR for both the noisy signal and the speech signal for all the three cases, spectral subtraction, Wiener filter, and Kalman filter. All these measurements are done in dB. As you can see, the power, the SNR for the Kalman filter model after cleaning the signal is the highest. So that is the end of this presentation. I want to show the implementation using MATLAB that I will show right now. So this is the Kalman filter modeling. So here we have read this input file and we have added a noise. So I'm going to show for color Gaussian noise. So what we try to do for getting the color Gaussian noise is you take this filter, and then you take first you define the white Gaussian noise as shown in this equation right here, and then you randomly pass it through the filter, and the filter's transfer coefficients can be defined as these. I randomly chose these values, and you get this colored Gaussian noise, and you add it to the original speech signal. Then you have to initialize all these matrices as shown over here, and then we can use the Kalman filter model to find the other parameters like the Kalman filter gain and error covariance for every iteration, and we get uh, the estimated speed signal as this parameter right here. So let me try and execute this. So this is for some random say 7. So this is the original signal, the noisy signal and the estimated signal. So the original signal sounds like this. Okay, something's wrong. Let me try using another. So the problem last time was I did not use sound of x comma fs. So I'm trying this again. This is the clean signal. Then we add noise to this signal. Becomes something like, it sounds pretty bad. And then we add the estimated signal. It's almost similar. And that's it. That brings us to the end of this presentation. Thank you very much.